Hey guys, in this video we are going to see how to interpret Oracle memory usage, and if someone complains saying that the database is slow, and when the DBA diagnose the issue, he is suspecting that it is due to Oracle memory pressure. Okay, so we already know that resource is the main culprit in any of the performance issues, right? CPU, memory, IO, network. So all these are interconnected, okay, but still they operate separately, right? So without CPU there will not be any processing of the tasks, right? So for any of the tasks there should be a processing power. So that processing power needs some area to process the data, right? So it needs some space. So that's what memory. So memory can give faster, you can say it can give space with faster processing power, okay. And if memory cannot be unlimited always, so to process all the data beyond a certain volume, then disk is required. So that's where IO come into picture, right? So from memory the data would be going to the secondary. We can call disk as the secondary storage. So swapping will happen if memory is not sufficient to process the data. And network, that is completely intermediate between the client and the server, right? And if there is an NFS file system, so that may also be having something related to network. So out of all these resources we are going to see the memory issue in Oracle and how to monitor and how to check as a DBA on what are all the things to check, and how to move our diagnosis during any issue. So as a DBA we need to ask all these questions, right? Before any issue happen, we need to capacity plan the server. How much RAM does the server have? How much RAM is Linux using? How much RAM is Oracle using? Is Oracle responsible for the memory pressure? Is a problem in the SGA or PGA? Is Linux swapping? So all these questions needs to be answered, right? So when it comes to memory usage, Oracle has divided the memory into shared memory and private memory, right? Which is SGA and PGA. So SGA can be used for all the shared memory components which can be reused, but for PGA it is used for individual private connections. So when the user process come and connect to the database, to the server process, the user process will be having a private area according to the architecture, right? So once it reaches the server process, it will go inside the shared memory where the shared pool will be there. So it will access all the SQL statements which are shared, the SQL statement details, right? The object details, the dictionary details, right? So for Oracle memory, memory troubleshooting is one of the common DBA tasks. So we need to understand how the memory is utilized. So first Linux physical memory, then kernel will be there, then Oracle process memory. This comes the logical layer, right? We know that instance is a combination of memory plus background process. So Oracle instance is a logical component. So we'll be having the physical RAM. So kernel will be the intermediate, okay, which communicate between the physical and the physical layer and the logical layer. So Oracle process memory will be the logical layer, and all these are the SGA components, and all these are the BGA components, right? So we can see the different scenarios, right? So the most commonly used command is free. So definitely we would have used in our Linux to check the memory usage, right? So you need to understand all these fields. So we have memory field and swap field. So in memory field we have total. So these are self-explanatory. So this is the total memory available on the server, 9 GB. Used memory is 0 because the current database is idle. And we have free memory, which is the amount of free memory which can be further used for processing. And if you see shared and buffer cache, right? So there are two different fields which are having some values. And there is also available. So what is the difference here, right? So we have separate column called free, and we also have a separate column called available, right? And we also have a separate column for buffer cache and shared. So how you can interpret these? So say for example, so in this example I have just given the machine physically having a 64 GB and Linux reports 30 GB currently in use. This does not mean that applications are using 30 GB, right? So here used memory is 30, but that does not mean that application is using 30 GB of memory. But here since there is no activity, this is 0, so that's why I'm giving an example of a different system which was busy, okay? And Linux includes all these subcomponents, right? So when it comes to memory usage, it is not only about Oracle using the memory, it also reserves for the other operating system usage, like the kernel memory. For interacting with the hardware controller, kernel also will be playing in the background. It also has its own tasks, okay? And there is a file system cache, and we have buffers and other processes. So all these are included as part of the used memory, okay? So here usage, that does not mean that Oracle has used almost 30 GB. So it includes every operating system memory usage as well, right? So 8 GB is completely used here. 8 GB is completely free here, right? So Linux cache frequently accessed files. So that's for this buffer cache. So here also we can see the buffer cache, right? 4 GB of data is cached in the memory. So like how Oracle buffer cache catches the data, operating system buffer cache also will catch the frequently accessed files. So say for example, so we have users01.dbf, okay? So this file, right? So this file would be accessed frequently by the database. So if you see this ls of process command, so you will be able to see how many processes are accessing the data files, right? And also specifically users 01.dbf. So here if you see, there are two processes which are accessing the users table space, the data file. And if you see system, so there are a lot of processes which are accessing the system data files, right? So these files, obviously when the Oracle database is up and running, definitely there will be a pointer from these background processes to the files. So obviously these processes definitely would be accessing the header of these files. So these are these processes should always be accessing these files, system data files, right? So system data files are the critical files in the Oracle database. Without system data files, Oracle database cannot function. So this includes the bootstrap data and all the data dictionary and all these, right? So these information, right, these files which are accessing the file, these background process which are accessing these files needs to be cached somewhere in the memory. So that's where you get this buffer cache as the 4 GB. Okay, so this is not only about system data files, it's about all the files on the operating system. So those will be occupying the buffer cache for faster access of the files. Otherwise, Linux has to again, similar to how in Oracle we do a hard parse, right? So likewise, Linux also has to again find the file location, find the header information, the process has to locate the address. There are a lot of things that will go in the backend. So for that purpose, we cached these file access. So yeah, this is an example. So archived log file, data file, trace files, binaries, everything would be accessed frequently. So those files would be using the memory from the buffer cache. And Linux will automatically reclaim if an application needs more memory. Okay, so I was just searching command. Okay, so there is a command in the Linux which can flush all the contents from the operating system cache. Okay, so that was what I was trying to check. Yeah, so we have this drop catch. Okay, so this drop catch is the command which will remove all the contents from the operating system buffer cache. Okay, so these things you may not be doing in a production system, but you can try it in your test systems. And if you are troubleshooting any critical issues, and if you want to flush the buffer from the operating system side, you can just execute this command. Okay, so this should be executed with the root access. So this cache memory is generally available Okay, and Linux estimates it immediately, provide about 31 GB to applications without swapping. Right, so from the operating system perspective, swapping can be prevented by buffering the data. So if this buffer is not available, if it is not sufficient to cache the data, then swapping occurs. So swapping will always be slower than processing in the memory, like how Oracle is processing the data from the buffer cache, right? And doing an I/O is expensive in the Oracle database perspective. So similarly, this I/O can be compared with the swap from the operating system side. Okay, so physical I/O, that is not logical I/O. Physical I/O is expensive, right, in Oracle database. So mem total is the installed RAM, mem free is the unused RAM, usually very small on Linux. Okay, and mem available is the amount of memory that is actually available. So this is where the actual difference that we need to understand, right? So mem available contains all of the memory that is available, that can be released, right? So this is an estimated metric. So here if you see, so we have available and free. So free is the exact free memory, which means none of the process is using, completely the memory is reserved for usage. But available is the metric which can tell that if any application can release any memory, this much amount of memory will be available. Okay, but we cannot say that exactly 5 GB will be available. Okay, but free is guaranteed available memory. Available is predicted or estimated available memory based on the application usage. So if any of the application has already done its processing and those memory or those pages are being cleaned up, right, for the reuse, then these memory can be 5 GB. Okay, so yeah, it calculates like you can say 3 plus 2, right? Free memory plus shared memory, 5 GB. And cached memory is the file system cache, right? So this is a buffer cache. So similar how Oracle uses the buffer cache. And suppose Oracle reads a data file, Linux may cache the blocks instead of disk. Okay, so Linux serves it directly from RAM and buffers metadata cache. So usually much smaller than cache. And huge pages. So huge pages is a separate memory allocation. This is not by default allocated, but we need to enable this huge page. So for all larger databases and data warehousing systems, we enable huge page. So huge page will be having a default of 2 MB page size, so which can allocate a huge size of page. So this huge page will be able to support the whole SGA size. Okay, so here Oracle is just multiplying the huge page total into the huge page size. So that's how it calculates the total huge page memory. 24 GB of huge page is available. So this is the probable SGA size. Okay, so huge page is not from the Oracle database side, it is from the operating system side. So once this huge page is allocated, this SGA will occupy space from the huge page. So if huge page is not there, then by default we need to use the operating system memory without any large pages. So by default the page size will be small, and Oracle commonly allocates the SGA using huge page. Okay, so this can be an interview question. What is the default page size for the huge page? It is 2 MB. Okay, so the next one is Oracle processes. So how you will check the Oracle processes? Right, so this is one of the most commonly used process query to check all the Oracle processes which are running. And next one comes the memory utilization. So how much memory is utilized by each and every process. Yeah, so here if you see, I just tried sorting the memory usage. So the first one is the PID, the second one is the RSS, which is the actual physical memory. Okay, the third one is the virtual memory. Okay, the fourth one is the command. Okay, command or the process name. Okay, so here the order should be RSS, VSG, PID, command. Okay, so what I'm saying is just sort the memory, sort the processes which consume the high memory. So here if you see, log writer is the process which is consuming more residual memory. So RSS is the residual memory and VSG is the virtual memory. Okay, so this is how we can break up all the processes which consume the memory, right? So here is the explanation. So we know all these background processes, and each background process has its own PGA, right? So if you see, this is the sample output. So RSS is the resident set size. So this is the actual physical RAM currently occupied by the process. Okay, so here also you can calculate this. It's if you see, it's almost consuming 582 MB of memory, okay, from the physical RAM. This is specifically log writer process. So next comes the virtual size. Okay, so virtual address space includes the allocated memory, map, shared memory, libraries, reserved memory. So we already know that what is virtual. So virtual means the memory pages that are allocated, right, from the operating system level. So these are not the actual physical RAM. Okay, RSS is the actual physical RAM memory. So virtual is the virtualization that happened on top of the physical, and these are the components. Okay, so we know that the libraries from the Oracle home will also be used as part of the Oracle database, right? So every library will be consuming virtual memory. So we also have shared memory segments, right? The semaphores. So if you just execute this command, you will get all the semaphore information, shared memory segments. So these comes under the virtual memory. Okay, and why RSS doesn't match the Oracle PGA? So we know that RS is the physical resident set size, physical memory. Oracle background process is attached to the SGA. Okay, so SGA is shared by every Oracle process. So RSS contains PGA, shared SGA pages, shared libraries, executable mappings. So it does not represent only PGA. So it is a combination of everything, SGA and PGA. Okay. So that's the reason RSS value is not equal to Oracle PGA. Okay. So we need to calculate the combined size of every processors. So that's why Oracle memory views are needed to measure the PGA accurately. So we don't rely on the RSS value to measure the SGA or PGA size. Okay, so yeah. So we can also calculate the total memory as well. So you can just write some shell script to calculate the total memory, total residual memory which are consumed by the Oracle background processors. Right, so somehow we can so yeah, you need to iterate all these processes. So I'm just giving you an idea. So you can use a for loop, and you can use the BC for calculating the sum of these different rows. Okay, whatever value that you get, you can just compare it with the Oracle SGA target and the PGA target. Okay, so yeah, next comes the PMAP. So PMAP is a process mapping command. Okay, so if you want to specifically map any PID of a process, so say for example I am just mapping this PMON process. So how much memory it is consuming overall, right? So you will get when you use the PMAP process mapping command. Specifically use the PID of the process. Okay, so these are all the columns: total KB, residual set size, residual set size, dirty pages. And next comes the semaphores, IPCS. We already seen. So this is very important command. Okay, so this shows all the shared memory segments from the operating system level. Okay, so you can also check the SGA information. Okay, so if you just give a -p command, you will be getting the CPID and the LPID information. So this process will be created by Oracle, but you will not be able to find this process if you just try to use PS or any other command. Okay, so this keep on changing every time. Okay, so now there is no activity, but yeah, so these CPID and LPID will be changing. Okay, so let us see what are all these information. So the bytes column shows the size of the shared memory segment. Here if you see the previous command, these are the shared memory segments. Okay, so which are allocated for the Oracle user. Okay, and each and every segment would be having a separate shared memory ID and also a key, unique key. Okay, so but here if you see, all these first three shared memory segments are having the same key. Okay, and these processes would be utilized by the Oracle SGA. Right, so CPID is the process that created the shared memory segment during the Oracle startup process. So this is a CPID is the starting process and LPID is the last process that is attached. Okay, so this CPID will be only used during the startup process. So after that you will not be able to find this process, as I already mentioned, right? So if you just see PS-EF grep this process PID, you will not be able to see these processes. Okay, yeah, so IPC key is used to identify the segment, which is usually indicates the segment which was created with IPC private. So SSM ID, owner, permissions for the owner to have read-write access to these segments, and size of the shared memory segments, number of processors currently attached to the segments. So almost, if you see here, 106 processors are attached to these segments, and remaining 3 are having 53 processors attached. Okay, so these are internal Linux concepts. Okay, so we don't go much deeper into it. So whenever we are going for a troubleshooting sessions, we will be going deeper, right? So when we are explaining these, there is we can say these are not of that much that you can understand, right? So even explaining normally will not help us. Only during the troubleshooting phase it will help us. So from the Oracle side, how you will check the memory usage, so that is very important, right? So how you will check this total size of the SGA? So we have a view called $SGA, which can help us in showing the size, or we can use the show parameter SGA. So we have SGA target, which is having the same size, and also SGA max size. So here SGA max size is the hard limit value, or you can say the capped value, and SGA target is the soft limit value. Okay, so we can modify the SGA target to any minimal value. So I can also modify it to 2 GB or 2 GB. I don't need a restart. But when I modify SGA max size, I cannot modify when the database is up and running. Okay, I need to restart the database. Okay, so that's the main use of SGA target. SGA target is the soft limit or the lower limit or minimal limit, and SGA max size is the harder limit. So SGA target cannot be greater than SGA max size. So if I just set SGA target to 3000 MB, it will say SGA max size is exceeded. So a specified value of SGA target is greater than SGA max size. Okay, so this is the hard cap, the capping value. So now we can compare the value of this VWSGA with the IPCS-M command, right? So previously we checked the semaphores, right? So just add all these values, you will get the SGA size. So all these values are in bytes. Okay, I'm just adding all these bytes value divided by MB. Right, so when you add up all these values, you are getting the size of the SGA. What is the size of the SGA? Same, 2.9 GB. Okay, so now you understand, right, why these shared memory segments are spawned in the operating system. So these segments are used by Oracle to allocate the SGA memory. Okay, so yeah, so if you just see select star from VWSGA or show SGA, you get all these memory allocations, right? So we have a fixed size, we have a variable size, we have a buffers, redo buffers, and total SGA. So total SGA is the total amount of SGA which we see here, and we also already know that we have a buffer cache, right? So database buffer cache is occupying this much amount of memory, and redo buffers are occupying. So these are online read log files and log buffer, right? Not the online read log file, this is log buffer. Okay, for the log processing, and this is a variable size. So variable size means Oracle can shrink or grow the memory. So fixed size cannot be shrinked or grown. Okay, these memory are reserved for a specific purpose. Okay, so you can check in VWSGA. Okay, what are all the fixed, what are all the variable components. VWSGA stat as well. Right, so shared pool comes under the fixed value, the fixed memory. Okay, so there are certain components in shared pool which cannot be shrinked or grown. Not all the components from the shared pool, but there are few components which needs a reserved memory. Okay, and next comes the SGA, VWSGA dynamic components. So here if you see, we have shared pool, large pool, Java pool, streams pool. These all are dynamic components. Okay, so these memory pools can be grown or shrinked as per the memory requirement. Okay, but there are few components inside the shared pool which cannot be removed, which will be quite constant. Okay, not all the memory pools can be flushed. Okay, yeah, so these are the parameters: show parameter SGA, show parameter PGA, and how we will check the current PGA size. Right, so we have show parameter PGA aggregate, PGA aggregate limit, PGA aggregate target. So 1500 MB is the soft limit, and PGA aggregate limit is the hard limit. PGA aggregate target is the soft limit. Okay, and how much memory that is total allocated for the use for sorting, hashing. 317 MB out of this 1500 MB. Okay, so similar to how we can modify the SGA, we can also modify PGA aggregate target. So I can also reduce it to 1000 MB, but I cannot modify this parameter when the database is up and running. Okay, so I will just say 7000 MB. Oh, okay, so PG aggregate limit also can be modified. Only thing is PG aggregate limit cannot be less than 6000 MB to this much. Okay, Oracle had made a standard that PGA cannot be set to a lower value, but this is a dynamic parameter. We can modify it when the database is running. The only thing is it was related to SGA. So SGA hard limit cannot be modified. Okay, but PGA hard limit can be modified. Okay, so next comes the PGA stat. So PGA stat gives all the statistics related to the PGA. Okay, so how much memory that is allocated for each and every purpose. So inside PGA we have a lot of other purpose, right? So PGA can be also used for work areas, for allocating the private memory for a session, and PGA can also be used for aggregation, sorting, hashing. A lot of different reasons PGA can be used, right? So these are all the different purpose of using the PGA. Each and every component are having a memory allocation, right? So this is just a test case, right, to understand how the PGA grows. Right, so if I create a table, and I'm just executing this select query, now we can monitor the PGA usage using this query. So now you can monitor this with this query. Okay, so how the PGA usage is happening. So when you execute any select query, right, then only we'll be able to understand how the PGA is utilized. So I'm specifically using order by object name, so to sort it intentionally. Okay, so now if you see, total PGA in use is increasing, right? So earlier it was 265, then it became 290, right? So you can monitor like this. So total PGA allocated is reduced. Here total PGA allocated is 340. Yeah, it's increased, it's not reduced, right? The maximum PGA allocated is also increased when I execute the query. So this is how you can monitor the PGA dynamically using this runtime query. So next I'm going to flush the shared pool. This is a shared pool test case. I am flushing all the components from the shared pool. Okay, now I'm just going to execute a loop query, a loop PL SQL procedure. Now you can carefully watch and monitor all these components. Okay, these will increase the moment when you execute the procedure. So currently we cannot specifically monitor any components, but definitely there will be a growth in the shared pool. Okay, so library cache usage will increase when we execute a PL SQL procedure with the multiple loops. Okay, so next comes the buffer cache. Just flush the buffer cache. So just do some select star from DBA source. Now monitor the consistent gets from VDAL buffer pool statistics. Okay, so the table is not that big for the buffer DB block gets to be increased. Okay, so otherwise this should increase. Let me do one thing. Let me flush the buffer cache again. Okay, yeah, so now if you see, there's an increase in the physical read and also the consistent gets, right? So there is a change. DB block get is same because this is a select query. Okay, so but physical IO and consistent gets are increasing. Oracle is using undo to get the consistent blocks. Okay, so this is how we can monitor the buffer cache, and how you will check the memory allocated for each and every sessions. So session level. So there will be multiple sessions, but you need to understand which session has consumed more memory, right? Okay, so this is also a useful query where you can check how much PGA memory that is being consumed by each and every session. Okay, so PGA used is the amount of PGA being currently used. PGA allocated is the allocated memory for that session, and PGA maximum is the maximum memory used by the session. So allocated memory is the memory allocated for that particular process. Out of this allocated memory, how much memory is used, right? So here if you see almost, so we can also convert this. Okay, so each and every memory, each and every session is consuming almost 1.9 MB. So each 1 MB these sessions are consuming. Okay, so this includes both background and the foreground process. Okay, so if you want to know which session is consuming more or allocated, if you want to group by, right? So I need to know which session is consuming more memory, PGA memory. So I will just order by this. So here if you see, M1 is the process which is consuming more memory, and archiver process. Okay, related to PGA, more PGA memory is used. So next comes the memory advisor. So this is also one of the important feature, right? So this view will give us the advice on size. Okay, how much size my SGA should be and how much size my PGA should be. So if you just check both these advisors, one is the current size. Here also one is the current size. Okay, so currently what is the size of our memory? Show parameter SGA target. It is 2000 MB. So if you see 1, size factor 1 is the current size. So here also 1 is the current size for PGA. So this is 1 GB. Okay, and how you will know whether we need to increase the SGA and PGA? Okay, so what you need to do is you need to check the physical reads which are reduced and also the time factor which is reduced. So here it is 1. Okay, for 1 the time factor is 1 and this much amount of reads are there. And if I go to 1.25, which means if I increase my SGA to 2500, I don't get any benefits. So after 2000, if you see, everything is same, the physical reads and the size factor. Only when I reduce it to 1500, I may get more physical reads and TB time would be increased. So I would not reduce my SGA. Okay, so if my SGA size currently, if it is 1500, then I should increase it to 2000. So then I will get the benefits. I will reduce my time by 1.2 to 1, and here I will reduce the physical reads from 41,000 to 36,000. So similarly, here also you have to see how much reads can be reduced, how much extra processing can be reduced. Here also I don't get any benefits. So after 1 GB I don't see any improvements. But if you see before that, if you set your PGA to 130 MB, we get this much amount of byte processed overhead. So if my current PGA size is 130 MB, I have to increase it to 520 MB. Then I will reduce these extra byte processing. Also cache hit percentage is reduced. So I have to target 100. So that's how you need to size your SGA and PGA. So this is another query to check the memory leak. So we already used this query. Okay. So again I am using the same query. So you need to understand in order to know whether there is a memory leak or not, right? So first, whether M1 process actually consume this much amount of memory, 85 MB of memory, that we need to understand, right? So say for example, if M1 is consuming 1 GB of memory, okay, then we need to further investigate why 1 GB of memory is being utilized by a background process. So that is not normal. So there can be some memory leak, right? But 85 MB is it's not that much high for a background process. Okay, so yeah, you can just compare everything from the operating system and the database just for your understanding, right? And from the total size level and also the session level. Okay, so these are all the ways that you can monitor the memory usage in Oracle database.